Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about mean value of a Poisson random variable, mean square value of a Poisson random variable, and variance of a Poisson random variable. And first, we are going to discuss about Poisson distribution expression. So we know that random variable capital X is a Poisson random variable. Then the Poisson distribution of a random variable X is given by probability of X is equal to M is equal e power minus lambda power M by M factorial for M is equal to 0, 1, 2, 3 and so on infinity, or probability of X is equal to X is probability of X is equal to X is e power minus lambda into lambda power X by X factorial for X is equal to 0, 1, 2, 3 and so on infinity. So where small x is or small m is the value taken by the random variable capital X. So this is the expression of Poisson distribution of a random variable capital X. So this expression is already derived, already explained my previous videos. First we are going to discuss about mean value of a Poisson random variable. So we know that the mean value of the random variable capital X is expectation of X or M is equal sigma X is equal to 0 to infinity X into probability of X is equal to X. So now here X is equal to 0, 1, 2, 3 and so on infinity. So X is equal to 0 to infinity. So what is the expression of the binomial distribution? Binomial distribution of a random variable probability of X is equal to X is e power minus lambda into lambda power X by X factorial. That is the expression of the binomial distribution of a random variable, and substitute that expression into here on RHS side of here. We get expectation of X is equal sigma X is equal to 0 to infinity X into e power minus lambda into lambda power X by X factorial. So X factorial is written as X into X minus 1 factorial, and lambda power X is written as lambda power X minus 1. And after that substitute X is equal to 0, substitute X is equal to 0, 0 into something, 0 into something 0. The first term in the summation is 0, that is for X is equal to 0. Substitute X is equal to 0 in this equation. The first term in the summation is 0. So substitute X is equal to 0, the first term in the summation is 0, and the remaining values of X is equal to 1. So therefore expectation of X is equal lambda into this lambda power X is written as lambda into lambda power X minus 1 e power minus lambda X divided by X factorial is written as X into X minus 1 factorial, and the remaining values of X is after substituting X is equal to 0, X is equal 1 to infinity. So this is the remaining RHS term. So now here numerator and denominator X is the cancel. RHS term of this equation is written as expectation of X is equal lambda into e power minus lambda sigma X is equal to 1 to infinity lambda power X minus 1 by X minus 1 factorial. So now substitute different values of X. So first substitute X is equal to 1 lambda power 1 minus 1 by 1 minus 1 factorial. So lambda power 0 by 0 factorial is 1. Lambda power 0 is 1 plus next substitute next value of the X is equal to 2 lambda by 1 factorial. Substitute next value of the X, we have lambda square by 2 factorial plus and so on. So substitute different values of X, we get the expression is 1 plus lambda by 1 factorial plus lambda square by 2 factorial plus and so on. So this within the bracket term is the expansion of e power lambda. So therefore e power X is equal lambda e power minus lambda into within the bracket term is expansion of e power lambda. E power lambda into e power minus lambda is e power minus lambda plus lambda. So minus lambda plus lambda is 0, e power 0 is 1. So therefore expectation of X is equal to lambda. So this is the expression of mean value of the Poisson random variable. The next one is mean square value of a Poisson random variable. So we know that the second moment of a random variable is expected. We know that the second moment of a random variable expression is expectation of x square is equal sigma x is equal to infinity x square into p of x. So random variable capital X is the Poisson random variable. The expression of the binomially distributed random variable expression is probability of x is e power minus lambda into lambda power x by x factorial. Substitute that 1 into here on RHS side. We get expectation of x square is equal sigma x is equal to 0 to infinity x square into e power minus lambda into lambda power x by x factorial. So substitute, okay. So now here on RHS side, by adding and subtracting by x, we have x square minus x plus x. So this within the bracket term is written as, so x square minus x, take the common x into x minus 1 plus x. Okay. So multiplying e power minus lambda, lambda power x by x minus x factorial into within the bracket term, and applying the summation into each term, we get the RHS term of this equation is sigma x is equal to 0 to infinity x into x minus 1 into e power minus lambda lambda power x by x factorial plus sigma x is equal to 0 to infinity x into e power minus lambda into lambda power x by x factorial. So now here in the first summation term, first term, substitute x is equal to 0, the term is 0, and substitute x is equal to 1, the term is 0. And second term of this equation is mean value of the Poisson random variable. So the mean value of the Poisson random variable already derived. So that mean value of the Poisson random variable is lambda. So therefore, substitute x is equal to 0 and x is equal to 1. The first term in the summation is 0, and the value of the second term is mean value of the Poisson random variable, that is lambda. So therefore, expectation of x square is equal. So after substituting x is equal to 0 and x is equal to 1, and the remaining value of x is remaining value of the x is 2 to infinity. So therefore, sigma x is equal to 2 to infinity x into x minus 1 into, so lambda power x is written as lambda square into lambda power x minus 2 into e power minus lambda divided by x factorial is written as x into x minus 1 into x minus 2 factorial plus second term is mean value of the Poisson random variable, that is lambda. So now here in the first term x into numerator and denominator x into x minus 1 is cancelled. So the RHS term is written as e power minus lambda into lambda square sigma x is equal to 2 to infinity lambda power x minus 2 by x minus 2 factorial plus lambda. In the first term, now we are the substitute different values of x, x is equal to 2 to infinity, we get the expansion is 1 plus lambda by 1 factorial plus lambda square by 2 factorial plus and so on. So substituting this summation, different values of x, we get this term. So this within the bracket term is the expansion of the e power lambda. Okay, so therefore expectation of x square is equal lambda square into e power minus lambda into e power lambda plus lambda. So e power minus lambda into e power lambda, e power 0, e power 0 is 1. So therefore expectation of x square is equal lambda square plus lambda. So this is the equation of mean square value of the Poisson random variable. And next we are going to discuss about variance of a Poisson random variable. So random variable capital X is a Poisson random variable. The variance of the random variable expression is, we know that variance of x is equal expectation of x square minus expectation of x whole square. So the mean value of the Poisson random variable and mean square value of the Poisson random variable already derived. So that are mean value of the Poisson random variable is lambda. Mean square value of the Poisson random variable expression is lambda square plus lambda. So this is already explained. Okay. And substitute expectation of x square. So in this equation we get variance of x is equal expectation of x square is lambda square plus lambda minus expectation of x is lambda square. So plus lambda square minus lambda square is the cancel, we get lambda. So therefore variance of the Poisson random variable is lambda. So this is the derivation, or this is the concept of mean value, mean square value and variance of a Poisson random variable.